Okay, sorry, I just cut that quick. So, swept-back wing development, that's what sweep-back gives you. It gives you increased lateral stability, right? In roll, it gives you increased directional stability. In yaw, it creates a smaller, weaker shock wave. It spreads the shock wave, it bends the shock wave back, and it means that the shock wave will not impact with a straight wing. Yeah, what you'll find is, if that's your wing there, and all your control surfaces are on the back of it, right, your shock wave will appear like that, and it'll move back, and at one point your shock wave will cover all the control surfaces. If you have a swept back wing where you have, if the angle of sweep of the front part of the wing is different to the trailing edge, and you have your control surfaces on the trailing edge like that, you find that your shock wave, as it moves back over into different positions, will never cover all of the control surface. Well, that's the idea anyway. Okay. These are all the sort of things you've got to think about. Right, where was I? Sweep back, yeah. That bit there leads to supercritical wings, okay, which I'll cover in the next part of the video. The last thing I want to talk about is anhedral, right? Okay, if you've got an aircraft going and it's got dihedral aircraft are prone to a thing called Dutch roll. Okay, what that means is the aircraft will start to, as it side slips and it corrects itself, yeah, and it's got that dihedral, you know, you'll sit, the wing is, the air is hitting that, it is causing a lot of lift on that wing, and it's also creating a little bit more extra drag, and that causes that up once it's corrected because of the dihedral. Remember, the pilot's not doing anything here. The pilot's sitting there, and the aircraft is righting itself because it's got dihedral wings. Why do Spitfires, Messerschmitts, A60s, P-47 Thunderbolts, why do World War II fighters have dihedral wings? Because they had to be stable gun platforms. You wanted something that would manoeuvre, but then you wanted something, when you wanted to shoot at something, you didn't want it rattling around and rolling too much, so you wanted it to be stable, yeah, to fire the guns and then go back in a dogfight. So your dihedral wings, the Hurricane early on in the fight didn't have, it had straight wings, okay, but the Spitfire had dihedral. So dihedral was the thing that came and went in World War II. It's prone to, as the aircraft rights itself, it creates a little bit more drag on this wing, and it drags that wing back over. That wing's going back over. This wing, right, correspondingly goes forwards, and that increases, right, the flow over that wing, which increases the lift on that wing. So the drawback of a dihedral, it enters a side slip, it creates more lift but also more drag, pushes this wing forward, which creates more lift on that wing, and then that creates more drag and comes back over, and the aircraft does this. So whenever it corrects itself, it creates a little bit too much induced drag, right, and it pulls the wing back over, and then once it's finished pulling it back over, the other wing takes over and does that, and it kind of like swims backwards through the air like that, okay, that sort of motion, and that's called a Dutch roll. Now, to prevent a Dutch roll on a Spitfire, you're getting 300 knots and you get a bit of Dutch roll. Whoa. Pilot puts input into it, corrects it, job's a good one. If you take something like Concorde with a very long pointy nose, okay, when you get that Dutch roll effect, if you do get a Dutch roll, so if you had even straight wings or dihedral wings on a fast aeroplane, right, too much dihedral, you get that Dutch roll effect going on. But what happens is, remember, they found a problem, I'll have to research the proper name for this, but the engines of a jet aircraft are pushing from the back. They're trying to overtake the nose. So jet aircraft, when you've got shock waves and you've got things pushing back, causing drag on the aircraft, remember the engine's trying to constantly do that and push out of line. As soon as it pushes it out of line, you'll get air pushing on the fuselage, which will make that even worse, putting the aircraft into a spin. Okay, that's why faster aircraft need bigger tails to stop that happening. Okay, that's why your Tornado has a massive tail. Okay, talk about why Typhoon has a smaller tail, probably in another video. That's how I know that the fly-by-wire avionics on the Chinese copy of the Typhoon are probably not as good, because it needs a bigger massive tail and it needs vent bus strakes at the bottom to make it stable. That means the computers aren't quick enough and aren't good enough to keep it as stable as a Typhoon is. That's my take on it. I might be wrong. Okay, right. Anyway, and the Rafale. Let's not forget the Rafale and the Gripen if we're talking about Canard aircraft. So we're flying along like that, yeah. And what we'll have is we have a bit of Dutch roll going on. So if we have this Dutch roll, yeah, with a fighter aeroplane, yeah, we could, as you can see, as I'm rolling the aircraft and doing the Dutch roll thing, see the side surfaces of the nose which could push it out of controlled flight. So if it gets into too much of a Dutch roll, we end up with the aircraft at high speed. Imagine it at 600, 700, 800 knots. That happens and you end up with air pushes where it's not meant to, and the aircraft goes into a spin and departs from controlled flight. How to get rid of that is, right, you take away a bit of the stability. Okay, so in order to make it a little bit less prone to Dutch roll, you take away its stability and you give it a little bit of anhedral, which is a little bit of a downturn of the wing. The Typhoon is a bad example of that because it hasn't got any. It's got straight wings, but that's fly-by-wire. Most aircraft, the F-16, which I don't have a model with, a good example of this is the F-104 Starfighter and the Harrier. Okay, so I'll put on the F-104. Right. Now, the other thing that anhedral gives you is it makes it less stable. Why does the Harrier need anhedral? The Harrier needs anhedral because it has a low slung fuselage. And when we're talking about stability at high transonic speeds, the Harrier is a high transonic aircraft. It can't go supersonic. Okay, so we don't want it prone to Dutch roll. And the other thing we want is, the Harrier's like that. The low fuselage, if a Harrier had a straight wing, what you would find is, it might be prone to a bit of Dutch roll. Okay, but as well as that, it would be very difficult to dogfight with because it wouldn't roll very quickly, right? Because it would try to correct itself all the time. You'd be fighting this pendulum effect because the Harrier's engine is underneath its wing. So that pendulum effect of having the weight low down stops it rolling quickly. So to make it roll quickly, we take away any sort of dihedral effect, any sort of rating, and we give it, right? So the low slung fuselage gives it stability because of the pendulum effect, and we tune that stability down a bit to make it more manoeuvrable by giving it anhedral wings. Got that? That anhedral wing also makes it less prone to Dutch roll. Most aircraft that would be prone if they had straight wings, if you look at an F-16, an F-16 has a little smiley face kind of air intake at the bottom. Right, an F-16 has slightly downturned anhedral on the wings and on the tail. Yeah, most aircraft have that sort of thing going on. Right, an F-18, slightly anhedral wings. A Su-27 flanker, slightly anhedral wings. As well as that, large transport aircraft such as the C-17, right, and the C-141 Starlifter. So they fly at high transonic speeds. So the F-16 and the Su-27, they're all supersonic fighters. But high transonic speeds for the, so something like a C-17 Galaxy, not Galaxy, Globemaster, that has a low slung fuselage. It has a bit of anhedral on there because basically it's probably a bit too stable. So the way to tune that stability down is, instead of messing around when you put the wing, you just put the wing on and make it downturn a little bit. Okay, and that anhedral will make that aircraft less prone at high. It's got a high T-tail on the C-17. It will make it less prone, okay, to the Dutch roll effect as it goes faster. Right. So, what do they all do? Delta wings. They get rid of the problem of buffeting on the tail. The other thing that gets rid of that problem is an all-flying tail or a stabulator or a tail horn, which I'll cover in 2 seconds. Wing fences, sawtooth leading edges, vortex generators. They get rid of the problem, or they help with the problem of loss of control effectiveness due to separated flow over the control surfaces by creating a vortex over the control surface, because a vortex is better than, you can't have laminar flow because you're going too fast at that speed. So the Javelin was a high transonic aircraft, so we create vortex generators in front of the control surfaces to stop that separated flow. BTEC want you talk about wing fences, they can have the same effect by controlling the vortexes where you want them on that wing to cut down on your span-wise flow, to cut down on your induced drag, but also put the vortexes where you want them rather than just willy-nilly wherever they want to be. Okay. The other way of doing that, Concorde does not have wing fences. Two Delta aircraft, right, that do have this sort of problem. The Mirage has a big slot cut into the wing like that, okay, and that creates vortexes over there. That's how they get away with it. Right, so Mirage, at high angles of attack, the Mirage has a slot in the wing which allows some air through that comes through as a vortex, which appears over the elevons on the Mirage. Okay, and Concorde gets rid of that problem by having what you call and the Vulcan does this as well. Right, Concorde and the Vulcan have what you call a cranked delta, which is this sort of shape here, so that I think vortexes on Concorde like sort of are created mid-wing, yeah, at high transonic in that sort of shape there. Okay, and they basically break up. The other thing that vortexes do as well, if you've got a shock wave along here, the vortex will break up the shock wave. Or so I'm told. I haven't done a lot of research on that. I might be talking rubbish. I think that's what happens. Right, where were we? Area rule. Right. So Delta Wings, yeah, and an all-flying tail. Getting rid of buffeting on the tail. Might as well cover that while I'm on. You've got a standard tail plane or standard horizontal stabiliser with standard control surfaces like you find on a Jet Provost, and then down here you have a tailer-on. The tailer-on or a stabilator, where that's the pivot point there, and the whole thing moves up and down. Now in control, we did mention about tailer-ons. As the back end moves up, the front end moves down, which eliminates the need for balance tabs. Okay, because but it does make them a bit twitchy. Yeah. So fighter aircraft, yeah, love them. Other aircraft, it can make them a bit twitchy, and then you might have to put an anti-balance tab on the end of them. We're going back to control with that. We're talking about stability at the minute with high-speed flight. Right, so when your shock wave forms and moves back over, when your shock wave gets to here, right, on your standard aircraft, your standard flying control surfaces, and you've got some separated flow going on, right, yeah, you could put some vortex generators on here for your tail and things like that, all sorts of stuff. Remember, sorry about that, wait a minute, hang on, got a problem here. Your tail's an upside down airfoil on a lot of aircraft. So your shock wave will actually be on the lower edge, and your separated flow might be on the lower edge as well, right? It's still not giving you lift, but in this case it's downforce, right? So this is kind of knocking you downforce a little bit, altering your balance. But the main problem is on a standard aeroplane, that elevator on the back, which we'll just colour in green there for the minute, yeah, that elevator there. If that's under separated flow, is that producing any lift? Or will that have any effect when you move it up and down? You will lose control effectiveness, you will lose control in pitch. Your standard elevators on your Spitfire, in a dive, once the shock wave hits the elevator and lines up with the elevator and destroys the lift on the elevator, combined with separated flow on the tail itself, you will pull back on the elevator to pull out that dive and nothing will happen. Some Spitfire pilots reported the way it changed the airflow over the elevator, that it actually reversed the controls, so you had to push forward on the controls to come out of the dive. What probably happened with that was, the push forward on the controls, it pushed the shockwave even further back and gave them some control back. Yeah, momentarily forward and then back, and then they were able to pull out the dive. Yeah. Or what could happen was, if you pulled the elevators all the way down, it would stall the tail, and it would tail stall. If the tail stalls, it turns off the downforce on the tail, and it would go nose down, which would then, yeah, I didn't think that one through. Right, okay, but what we can see is, in high transonic speeds, if we get a shock wave and separated flow over the elevator surfaces, we will lose control. How the tailer-on and the stabilator get away for this, okay, is what they have is, if that shock wave happens in exactly the same place, yeah, the whole thing's moving up and down. So when the whole thing moves up and down, you've still got all this green section here, right, which will still be in laminar flow, which will still give you control over the aircraft. Okay, so tailer-ons and stabilators, all flying tails, are, they're not immune to control problems, but they are nearly immune to like shock waves and control problems affecting them. So you'll still have control at supersonic speeds, even if it's got a shock wave on it. Big shock wave right in the middle of a tail-on goes, it's okay, I've still got 80% effectiveness. Yeah? Okay. So, and it's not just on the back section of the tail-on, you have, like say, you have a big shock wave there on the tail-on, and a little shock wave on the top of it. You've still got plenty of tail-on moving in laminar flow, yeah, to still give you control effectiveness. Right, and now we'll leave it there. Okay. Yeah, we'll leave that for now. Right, so that's tail-on. So that gives, so delta wing gives you extra control. The swept wing and the delta wing gives you advantages. Okay. It stops you with the problem with tail buffeting and things like that. Right. Wing fences, vortex generators, they give you a control effectiveness solution. Area rule makes the shock wave go over the aircraft smoother and quicker, which means the shock wave's not hanging around causing problems, causing balance instabilities and things like that. It just forms on the wing and moves back very quickly. You want that shock wave to form as small as possible and move backwards as quickly as possible. Right? Sweep back helps you, we've just gone over that, it helps you with normal stability anyway, lateral directional stability, but it also makes that the shock wave move further back. It makes a smaller shock wave, it makes it move further back in easier, and it's less swept back wings. Yeah, we'll leave that for now. Some swept back designs are more prone to Dutch roll, okay, which because of how the stability works. So what we do is we give them a bit of anhedral, okay, just to tune down that Dutch roll. How anhedral tunes down Dutch roll is when the downgoing wing's going down, it doesn't create that extra lift, right? So an anhedral aircraft, when it's disturbed, will continue to be disturbed, and the pilot has to take control and right it a bit. So it's less statically stable than a dihedral aircraft. Right, any questions, pop them in the comments box, okay. I'll do a little bit more on the last video. We'll do a bit on how to damp out longitudinal phugoid motion, and we'll do that very shortly. Good luck with that. It's not as hard, we're just going to talk about supercritical wings. Thanks for watching. Okay, comments below the video, subscribe to the channel if you like the videos that you see, and good luck with your assessments. Thanks very much.